Okay, thanks a lot for the invitation and for joining. Yeah, so I'm going to talk about rough walks, which is a combination of rough path topology and stochastic processes like random walks in random environments. And I will explain. But before I'm going to explain, I cannot assume that people are familiar with the rough path topology and rough path spaces. So I will give you just a taste of it, just that you will have something to keep in mind, and it will be helpful for the rest of the talk. Okay. So the motivation for rough paths is coming from the notion of universality of Brownian motion. And okay, I think it's better now, right? And yeah, okay. So we're all familiar with on-scale invariance principle. It tells us that if you have a random walk, the sum of IID random variables with mean 0 and variance 1, then if you diffusively rescale the random walk, meaning you speed up time by n squared and you divide by n, and either you take the Cadillac version or you take a linear interpolation of that so that you have a continuous path, both of them are going to converge to the standard Brownian motion. In the Stochastic topology, weakly. Yeah. So this gives us an idea of a notion of universality for Brownian motion. It doesn't care about the details of the random walk. As long as you have these two conditions, then it will converge to the same Brownian motion. Okay, that's great. However, if you would like to approximate a stochastic differential equation, so let's assume that you have a stochastic differential equation of this form, so it's in an integral form here. An observation by Wong and Sakai from 65 is telling you that if you do the naive thing, so you want to take, instead of the Brownian motion, the integral with respect to the Brownian motion, you're taking the random walk, so you're solving this difference equation, we scale, okay? Then it will converge to the solution of this stochastic differential equation. So it is an approximation of this stochastic differential equation where the integration here is with respect to the Ito integral, okay? Now, on the other end, if you take now the linearly interpolated path of the random walk, then this is an absolutely continuous path. So you can define the Riemann-Stieltjes integral. And in particular, you can define this equation here. And if you solve this equation, it will converge to a difference, an SDE, but it's going to be a different stochastic differential equation. So we're going to have a drift term here. And this is going to be actually the Stratonovich integral here. Okay, so two different approximations of Brownian motion give us two different solutions. So in other words, it tells you that the Ito map taking the noise to the solution is not continuous in the Stochastic topology. And okay, so this is a problem of universality. It said that it's universal. On the other end, there is still hope to get universality because we still don't care about the details of the random walk. We care about the approximation. So it means that it leads to rough path in the following sense. Rough path is taking the notion of integration into account in the definition of universality, okay? So here is a definition of a rough path by Terry Lyons from 98. It's a p-variation rough path. And this is a pair, a first level and a second level, that is defined via increments or generalized increments, so pairs of times s smaller than t in an interval, so that the first level is in RD and the second level is a d by d real matrix. So that the first level is indeed an increment of a path. And they satisfy these two conditions. The first condition is an analytic condition. And what you want is that the first level will have a finite p-variation norm, And the second level, we will have a finite P over 2 variation, whatever that means, okay? Another condition, and this is an algebraic condition, it is a relation between the second and the first level. It's called the chance relation. So this is for any S smaller than U, smaller than T. And when you have these two conditions, you can define a notion of integration. And now, before I'm telling you that, let me just explain what you need to have in mind. So the point in this definition is that this second level, you should think about, you should think it is morally as the iterated integral of the path. Okay, so it's an integral of the path with respect to itself. And it has a notion of integration inside. So it keeps the notion of integration in the definition. It turns out that all you need is this in order to understand what's going on. And I say morally, so I mean that every notion of integration will satisfy the chain relation, but you don't need it. So you just need the chain relation. Okay, so this is a definition of P variation rough path. And if you are not so familiar with P variation rough path, this is essentially, this is a parameterization-free version of the Helder norm, okay? So just to have something in mind, okay? And if you have this definition, the theorem by Lyons and Gubinelli is telling you that if you now have this rough path, then you can define integration with respect to the rough path for a large class of y's, I don't want to specify, and so that this map taking the function y and the rough path to the integral is continuous in a suitable space. And moreover, you can solve this equation in a certain space so that this map taking the noise to the solution is continuous in a suitable space, okay? And this is in particular telling us that if you know that you have a convergence in the rough path topology of the noise, if you have an approximation of the noise, then you have convergence also of the solutions. Okay. So that's just a bit, a taste of rough path, okay? Let me now explain what I'm going to tell you in this talk. So this is a program that we have in which we lift random processes to the rough path topology in the context homogenization. So we're interested in functional CLTs, okay? And this has applications in two areas. One area is SDEs, so you get non-trivial approximations to the noise. And you want to understand how the solution behaves when you have different approximations of the noise. And another area is random media, random walk in random media. So here you get, so you have a functional CLT in the rough path topology, and it gives you a richer picture of the limiting path, okay? So you get more details. And rough path was an inspiration to the theory of regularity structure. Okay, so rough path theory is dealing mainly with SDEs. Regularity structure is dealing with SPDs, singular SPDs. And the hope is that you could, in the future, take all of this and extend this type of perspective also to these to particle systems and SPDs, but that's just in the future, the motivation. And what we will see today that this program is achieved for regenerative processes and additive functionals of Markov processes. And these are two extreme big classes of processes that cover in particular two classes two of the most fundamental classes of random walks in random environment. And this is where my motivation, my personal motivation came from. And lastly, I want to mention that I mentioned this richer picture that you get in the limit. So I want to mention that it reveals asymmetries of the system. And I use reveals because you cannot see them in the usual CLT. And I will explain, okay? So to have one application of rough path and this continuity, let me present a theorem by Kelly that is telling you the following. So let's assume that you have a sequence of semi-martingales, or martingales if you wish, okay? That you take the Stratonovich lift, so you take the iterated integral with respect to the Stratonovich integral, okay? And let's assume that they converge to an enhanced Brownian motion, okay? Or a rough path, so that the first level is a Brownian motion, and the second level is the Stratonovich iterated integral of a Brownian motion corrected by a certain linear function. So you have a gamma here, which is a d by d matrix, and that's the structure of the second level, okay, for S and T. Then, if you take a nice F and you solve these equations, these Stratonovich SDEs, so no rough path topologies, just the Stratonovich SDE, okay? Then they will converge to this Stratonovich SDE. So naively, you would expect, if you don't know all of this, so maybe naively you would expect that it will converge to this one, but you have a correction, you have a certain drift that you can write explicitly in terms of gamma, okay? And well, this explained the first slide. So it explained, for example, the difference between Stratonovich and Ito, right? Because you can always write a Stratonovich as Ito plus 1/2 the identity, essentially. Let me give you another example that is less trivial and more, it's the simplest example that I could come up with that is more in the direction that we are going now. So let's take two processes on Z2, okay? And what I want to do is I want to couple them. I want them to go together like that. So first 4 steps, they're going to do a simple random walk, okay? So let's say, I don't know, 1, 2, 3, 4. And this guy together with the left guy is doing the same thing. And then the right guy is going to stay for 4 more steps in its position, while the left guy is going to do a loop, clockwise loop, starting from up, okay? And then you iterate, okay? So 4 more steps that are going to do together a simple random walk. The left guy is going to do a loop, and the right guy is going to stay for 4 steps. What is clear, that let's call this guy X and this guy X bar, I don't know, and let's diffusively rescale them. What is clear that both of them are going to converge weakly to the same Brownian motion, right? Because this loop is so small that you don't see it if you rescale. However, if you take these linear interpolations, right, and you take the iterated integral, what you can realize is that they will converge to a different object. So this guy will converge to the Stratonovich iterated integral of this Brownian motion with a gamma equals 0. And this guy will have a gamma of the form some constant. It's going to be an antisymmetric matrix, and it's going to have something like that. Okay, I don't remember the constant, which is not 0, okay? So you're going to see different limits And this type of behavior you cannot see in the in the first level. Okay, so I keep this for you to have in mind. So this is like a very simple example, but let's take it to the to the next level. Okay, so let's consider regenerative processes. What is a regenerative process? It is a discrete time random process on RD, so that its increments form a delayed renewal process. What do I mean by that? There exist an infinitely many, almost surely infinitely many times, finite times, so that if you look at the process on a time interval, jointly with the size, with the length of the time interval, these are IID, starting from the first interval, and the zeroth interval is independent. Okay, so this is just to have some generality. So just to have a picture in mind, okay, something in mind. I don't know. It looks something like that schematically. So let's assume that we have some. So this is x0, x tau 1, x tau 2. Let's do another one, x tau 3. And the point is that you are looking at the path from tau 1 to tau 2. So this piece here, this is going to be independent of this guy and of this guy and so on, but they are going to have the same distribution. So they're going to be IID, and they are all going to be independent of the first guy to have some generality. Okay? Questions? Okay. By the way, feel free to ask as much as you want. Okay, a condition, a moment condition that we will need, we call it the second moment condition. A second moment condition is as follows. So what you want, you take the regeneration time interval, the size of the interval, and what you want is that if you take the deviation of the path on the interval, so this is always the increment. So just to make sure that you remember that, this is always, this is what I mean when I write that, okay? So you take the maximal deviation, the second, the square of the maximal deviation times the size of the length of the interval, and you want this to have an expectation 0, okay, for all k. Okay, k equals 0 and 1. And an example, if you want an example of a regenerative process, you can just take a random walk, a sum of IID random variables. Then you can just take the intervals to be of size 1, right? You have these independent pieces. They are all IID, so this is of size 1, and this is going to be exactly the second moment of the jump. So this is equivalent to the second moment condition for the random walk. Okay, so this is why it's called second moment condition. Now it's time to present the first result. So let's take a regenerative process X, satisfying the second moment condition. Let's assume that it is centered on the regeneration times, okay? It's expectation 0 on the regeneration times. Let's rescale diffusively and take a linear interpolations like that. And this is absolutely continuous. We can define the Riemann-Stieltjes integral. Let's take the iterated integral with respect to the Riemann-Stieltjes integration. And we get this Riemann-Stieltjes lift, okay? And a result with Olga Lopuzansky and progress by myself is telling you that for every p between 2 and 3, the p variation rough path topology, we have the convergence in law of this rough path to a rough path that has in the first level a Brownian motion. Of course, in the second level, you see here, this is a Stratonovich iterated integral of this Brownian motion plus a linear correction. And this linear correction, again, D by D matrix that has this form. It is called the area anomaly. And it is the expectation of the following matrix. This matrix is the antisymmetric part of the iterated integral on a regeneration interval divided by the expected size of the expected length of the time interval. Okay? And questions on the theorem? Okay, so let me give you some remarks. So the first remark is regarding optimality of the result. So this moment condition is optimal for this result. And as we saw, a random walk is satisfying, is a regenerative process. And for random walk, this is exactly the second moment condition. And this is known to be equivalent to a classical CLT. So you cannot get any better than that. This is optimal. Second, we saw that now if you want to approximate an SDE by a regenerative process, you have to correct it, and you know how to correct it explicitly in terms of gamma. And the last thing is, I mentioned that the name of this gamma is area anomaly. And the reason is that it has a geometric interpretation. So again, let me do something schematic here, although this is absolutely not, this is somehow misleading. Because usually you have expectation 0, so you should not see something like that. But let's assume that this is xi and this is xj, okay? And this is a time 0, x tau 1, x tau 2. Then in order to okay, so yeah, yes. So in order to compute the this area anomaly, what you need to do is you need to draw a line between these times in the time arrow, and you just compute the signed area above this line. Okay, so this is a plus, and this is a minus, and this is a plus and a minus. So you get a number. This is a random number. You take this the expectation of this number, you divide by the expected size of the interval, and this is gamma ij. So you see that this is antisymmetric, and you see that on the diagonal you have 0. Okay. Good. Now, some applications. So the first application, this is what we came from. So that was my main goal in the beginning. So you can apply it to ballistic random walks in random environments in dimension larger or equal than 2. These are IID, uniformly elliptic random environments that satisfy a certain ballisticity condition called the Snitman T prime condition. And you can see that under the annealed law. And to see that this is really an example, Snitman and Cerner proved that you have this regenerative structure. And Snitman later on proved that you have all moments, in particular the second moment condition. So you can just apply to ballistic random walks in random environments. And you can also apply to another class of random walk in random environments, the Dirichlet environments. And here, this is an example that you don't have all moments. You have just finitely many moments, but still, if there is a parameter that if it's larger than 3 here, then you still have this CLT and regenerative structure and so on. One nice and easy example that you can prove is random walk in periodic environments. So this is Z2, okay? So these are the edges of Z2. And let's assume that you have a periodic environment. So something like, so you have these boxes, and on the box, you have probability distributions to jump to nearest neighbors. And they are the same, the box here, the left box and the right box, they are the same probability distributions, okay? So let me draw a few more boxes. Okay. So if you have this, for example, and you want to prove a CLT what would you do? Okay, you want to prove CLT for that, what would you do? So a suggestion, let's assume that this is the origin. What you're doing, what you can do is you can say, well, I'm going to start my walk and wait until it arrives to the origin modulo the period, modulo the box, the first time. And this is going to give you this regenerative structure. And if these probabilities are all positive, then these times are going to have actually an exponential moment, and everything is going to work fine. You just need to recenter if you don't have expectation 0. Okay, so and so you will have this correction that we mentioned. You just need now to compute it, right? So you just draw a line and you can compute the expected correction. Okay, last example is additive functionals of positive recurrent Markov chains. So if yk is a positive recurrent Markov chain, irreducible, we can take define xn to be the sum from 1 to n of f on y. Okay, and okay. Then you just take the return times to be your regeneration times, and you just need to verify that you have a second moment condition. Okay, you can think about other examples, but these are a few examples. Now, okay, so I started lightly. I started with these processes that are very nice. So essentially, these are IAD-like processes, right? So on this regeneration times, you have a random walk, a sum of IAD random variables that you can believe that if you can control what the random walk did between 2 times and the size, that if the size of these intervals are not is not too large, then okay, then you can deduce the CLT, and I gave you the exact condition to that. Fortunately, many other processes, they don't have this feature. So for example, what you can look at is additive functionals of Markov processes that are not positive recurrent, for example, okay, that are recurrent but not positive recurrent, or that are transient. And these can have CLTs as well. And in there you need a completely different tools to deal with these guys. And the main motivation for me to all of that was the random conductance model, which is random walk in random environment in the reversible case. Okay, so you don't have anything near a regenerative structure there. Okay. So let me briefly explain about additive function of Markov processes. So an additive function of a Markov process, we are going to deal with the continuous time case. It's just going to be easier to present things like that. And this is a rescaled additive functional of a Markov process. So if X is a Markov process and F is a nice function, we are interested in this quantity, and we would like to prove that this converges to a Brownian motion. Okay, and so let me explain the main idea. Probably some of you are familiar with that, but just to have something in mind. So if you start with a stationary ergodic Markov process. You start from the stationary distribution mu. L is the generator, and F is from the state space to R, which is measurable and bounded. And let's assume that you can solve the Poisson equation in L2. Okay, so with respect to F. So meaning that you need to find a phi in L2 that satisfies this relation. And if you can do that, you can define the Dynkin martingale M like that. This is always going to be a martingale. Okay, it's not easy to see. And it's a well-known martingale that you can compute its predictable quadratic variation, and it is the time integral of this object here, assuming that everything is well-defined. And so now let's rescale diffusively the martingale. So if we compute the quadratic variation, then by the ergodic theorem, since we have ergodicity and stationarity here, this will converge to this expectation. Okay, and therefore now if we want to write the additive functional, rescale additive functional, so you see this minus L is exactly F. So this time integral is exactly this time integral. So you can just write it as a martingale rescaled plus this difference rescaled. And this difference, since we assume that it's in L2 and we assume stationarity, then this is just going to 0 and then goes to infinity. And therefore, you are left with proving a CLT for this martingale, but we know convergence of the quadratic variation, so we are done. Okay, so that's, if everything works, this is what you do usually in these cases. Now, solving the Poisson equation is too much. It's usually either difficult or just impossible. You cannot find a solution phi in L2, okay? But what people do is they solve the resolvent equation. So you take a lambda, which is positive, and you solve this equation. This equation is always solution in L2, even in L1, because this is essentially killing the process, killing the Markov process with an independent time of exponential time of expectation 1 over lambda. And if you solve this equation, what it turns out, and this is the Kipnis-Vardan method, that you could have that the second, the L2 norm of phi lambda is going to infinity as lambda goes to 0. Okay, so you don't have a solution in L2. But what you need is that it goes to infinity slower than 1 over square root of lambda. Okay, so this condition here. And you need another condition like that. So this defines a certain norm that is called the H1 norm. So you want that phi lambda is going to be a Cauchy sequence in this norm. It's written explicitly here. And you call this the H-1 condition. And this Kipnis-Vardan method is telling you that if you have the H-1 condition, then you have a CLT. And essentially, the way to prove that is you go back to that slide that, before, and you approximate, and you realize that you need these two conditions in order to end. So there are some observations there, and but that's the philosophy. And one thing that I want to mention is that it's always true in the case that X is reversible. So if L equals L star, then you always have these conditions. And in fact, Kipnis-Vardan considered only the reversible case, and then later on people understood that you don't need reversibility, but just this condition. Okay? So now I'm going to tell you about a result that we have. So we took additive functions of Markov processes, and we left them to the rough path topology. So this is a result with Jean-Dominique Deutscher and Nicolas Berkowski. And here we take a Markov process starting from stationary and ergodic distribution mu, which is also stationary and ergodic for L star. Okay, this is the assumption. And we have a function from the state space to RD, which is bounded and measurable with expectation 0 in all coordinates. And we assume the H-1 condition. And now let us consider the additive functional of the walk with respect to F, of this Markov process with respect to F, already rescaled, diffusively rescaled. This is an absolutely continuous function. So you can take the Riemann-Stieltjes integral. So you take this lift. And then the theorem is telling that you have a convergence in the p-variation graph path topology for every p between 2 and 3, weakly to this graph path. So again, you have a Brownian motion, a Stratonovich iterated integral, and a correction. And now this correction can be written as a limit as lambda goes to 0 of expectation of, so this is a d by d matrix, so this is a tensor, okay, of phi lambda, say phi lambda coordinate I times the anti-symmetric part of the generator acting on phi lambda coordinate j. Okay, so this is the anti-symmetric part of the generator. And it was known before that the Brownian motion has a covariance matrix, which is given by twice the same thing with the minus the symmetric part of the generator. So what you see here is, again, some anti-symmetry, okay? So you see that you have a correction in terms of the anti-symmetric part of the generator. In particular, if the random walk, if the Markov chain is Markov process is reversible, L equals L star, LA is just 0. So you have no correction. So this is a phenomenon. Having this non-zero is a phenomenon of anti-symmetry. Okay. And yeah, I mentioned the random conductance model. So let me just briefly, I guess that people are familiar with that, but let me just briefly define it. So we are looking at ZD, okay? And we are looking at edges, the usual, the nearest neighbors, nearest neighbor edges of ZD. So this is XY here. And we consider a configuration of conductances, weights, for every edge. Omega is omega xy is omega yx. So it's a bunch of weights, of conductances. And you call this an environment of conductances. And given such an environment omega, this defines a Markov chain, xt, continuous time, that jumps from x to y with rate omega xy. Okay, so this is actually written. And it was known already in '83 that you have homogenization. You have a functional CLT. So if you rescale, diffusively rescale the process, and you have a functional CLT, if you assume that these conductances are taken in an IID way, and they are uniformly elliptic. They are bounded away from 0 and infinity. And they converge to a certain Brownian motion with a non-trivial covariance matrix. Non-trivial meaning non-identity. This result is in the annealed case. So you average with respect to the environment. Okay, and it's important to mention that you have this reversibility, so you have no ballisticity. Okay, so you have a law of large numbers, but xn divided by n is going to 0. Okay, and typically people apply additive functional theory to random conductances in the following way. Okay, so they have a clear connection. So let me briefly explain. So if this is your random walk in the environment omega, environment of conductances, you can always write it as a martingale plus a time integral of a certain function f evaluated on a certain Markov process, a different Markov process. And this Markov process is going to be the environment seen from the walker. Okay, so it's going to be, you take your environment and you, whenever the walk is doing a step, you just shift the environment accordingly. So this is a Markov process on the space of environments. And this F is just defined here. It's the local drift. It's called the local drift. Okay, so you can always define that. And what is nice about this Markov process is that it is ergodic and reversible with respect to the initial IID law. Okay, if you assume that. Okay, so now when you have this presentation, so this is an additive functional of a Markov process. So usually what you do, you just prove you have a CLT for this and a CLT for that, and you just need to understand the covariance relation, and you do that, and that's it. And what we did, we lifted that to the rough path topology. So you need to take also the iterated integral. So you need to take, okay, so if this is the rescaling of these two objects, so what you need to do is you need to take the iterated integral of the martingale part with respect to itself, and you get this rough path convergence. But since this is a martingale, and if you take the Ito lift, then you get an Ito iterated integral. And this is an additive function, also we can use our Kipnis-Varadhan rough path theorem in order to lift the additive functional. So you get a Brownian motion, and here you have a Stratonovich iterated integral. And you see no gamma, no correction here, right? Because I mentioned that this Markov process is reversible. So you don't see a correction. However, you have a Stratonovich and an Ito, which is a hybrid. So if you deal still with, you need to still deal with the cross term, the integral of m with respect to z and z with respect to m. You do that, and then you get the theorem. So if you start from an IID conductances and they are uniformly elliptic, and you take the Ito lift, okay, the left point sum. And then you consider that in the rough path topology, you have a convergence in the p variation, the same story. To a Brownian motion, here is Stratonovich iterated integral, and here the correction, you have still have a correction, and you can write the correction explicitly as a diagonal matrix, which has minus the expectation of the weights on the diagonal. Okay. And as I try to hint, so you started from a Ito lift, so you cannot expect to have a Stratonovich integral in the limit. You have this hybrid thing, so you have a correction. But if you start from linear interpolations instead of Ito lift, then actually you don't see a correction. So it will converge to the Stratonovich iterated integral. Okay. Questions so far? Okay. So let me mention some deeper result in the random conductance model. Okay. Classically, okay, people used additive functionals of Markov process to prove functional CLTs in the case of random conductances. However, unfortunately, you can only get an annealed result. So when you average with respect to the measure on the environment, or in probability that in this case it's equivalent. Of course, additive functions of Markov processes is much more general than the usage for the random conductance model, right? So you don't have, in particular, you don't need to have a reversible Markov process, but unfortunately, you just get an annealed result. In order to get a quenched result, which means you want to sample an environment, a typical environment, and prove a CLT for that environment, and you want that the Brownian motion that you get in the limit is going to be determined with a deterministic covariance matrix. It's going to be the same for almost every environment. Then you need more. You need to understand better the space of random conductances. Okay, so I gave you some references here, but let me explain briefly what people did. What is their philosophy? What do I mean by understanding better the space of random conductances? So what people did, what you can do is you can find an Hilbert space on cross-cycle functions, whatever that is, on the space of environment times the physical space, the ZD, so that this Hilbert space, it has a direct sum decomposition to two subspaces, okay? So that now if you take, if you project on the position, so you take an environment omega and a position X in ZD to X, you can write down this decomposition of this pi according to these subspaces. And then if you plug inside the process, so xt is just the position of xt, right? You can write it down as in these two coordinate systems, if you wish. And it turns out that if you do that with this structure, you get a martingale for the first guy, and something that is called the corrector for the second guy. And what people do is they prove that the corrector is sublinear using heavy analytic tools. And they use that to deduce that if you diffusively rescale the process, then the corrector will vanish in the limit, and therefore you are left with the martingale part. And for that, you need to prove, you use the martingale CLT to prove a CLT for that. Okay, so you understand the structure of this martingale, and this is a quenched martingale. Okay, so that's the main idea of how to prove a quenched CLT for the random conductance model. So what we did in a work in progress with Johannes Boimler, Noah Berger, and Martin Slavik, we consider this perspective, okay, in the rough path topology again. And what we managed to do is first, we got an annealed result, so averaging over the environment, but for general conditions. So if before we had IID, uniformly elliptic, very restrictive. So here we have very general conditions. In particular, you can allow the jump to have long jumps. It can be stationary and ergodic and not just IID. Another thing that I want to mention here is that you know, I mentioned that the corrector, if you diffusively rescale it, then it vanishes in the limit. However, its iterated integral does not. And in fact, it converges, and you can write the limiting. It converges in probability to a linear function. And you can write this function in terms of the Hilbert norm of this corrector coordinate. And this relates to the correction that I presented using the Kipnis-Varadhan theory. So you have two presentations of the same object. Remember this diagonal matrix with minus the weights, the expected weights on the diagonal. Okay, so we have these two presentations of the same object. And we also get a quenched result. But quenched result is quite hard to get. And we get it only for ZD, D larger equal than 3 when you have IID, nearest neighbor conductances, that are bounded away from 0 and infinity or 0. So in particular for supercritical percolation clusters. We use the recent progress by Gloria Neukam and Otto, and by Paul Dario, is a postdoc in Tel Aviv, but they show that this corrector, it's not just vanishing in the limit, but it has all moments annealed, together with available quenched heat kernel bounds, we managed to take this estimate, which is an annealed estimate, and pushed it quenched to be taken uniformly in time, quenched. And when you have that, you can use the nearest neighbor assumption to push that also to the martingale part, and with these two things enhance just technical work, and you get also a quench result. Okay, so let me summarize. I mentioned a program that we have on homogenization of rough walks with applications to SDEs and to random media. The first application was to regenerative processes, and we applied that to ballistic random walks in random environments. Here we have an optimal moment condition, and we saw that there is an area anomaly that appears, and the correction can be identified in terms of a stochastic area. You can picture a stochastic area. Then we consider the the Kipnis-Varadan theory in the rough path topology, and we deduced that there is no area anomaly if the process is, the Markov chain is, or process is reversible. And you can apply it to random conductances, and there you see a correction if you take Ito lift, and no correction if you take Stratonovich or linear interpolation. Yeah, and I mentioned that you can extend this method to other models, so not just to random conductances. And lastly, we talked about the cross-cycle space perspective for random conductances specifically. There we got area anomaly in the Ito case, that the area anomaly in the Ito case can be expressed in terms of the H norm of the corrector, that Hilbert space that I mentioned. And it also annealed with general conditions, very general, and we can also get quench result whenever the corrector has enough moments. Okay, yeah, so these are papers that I mentioned. So the first one is on the ballistic random walks in random environments with Olga Lopuzansky. You can find it on the archive. Second one by myself on delayed regenerative processes. This is still in writing, but it will be ready very soon. The third one about additive functionals of rough path. This is with Jean-Dominique Teuchel and Nicolas Polkowski. It was recently accepted to Annals of Probability. And the last one with Johannes, Noam, and Martin, it's still in writing. Okay, that's it. Thank you.
Okay, thank you very much. Let's thank the speaker. Are there any questions, comments?
Maybe I have a question. So, for instance, in the last one on the random conductance set, right?
Yes.
So previous results on, can you explain again what are the results that you get? Are they also on just on convergence of a functional CLT, or do you get or is it just on the higher structure? Some of the previous results on CLT did not use rough path.
Right. Right. Okay. Yeah. So the point is that yes. So we extend the CLT. So proving a CLT in the rough path topology really contains the usual CLT. So we extend that, but you get a convergence to an object that has also a second level. That this Brownian motion has a second level. But this second level gives you more information on the object. So yes, so we have this area anomaly or no area anomaly on the limit. And let me mention something here that I didn't mention, but I think that it's important. So you can ask yourself, well, is this everything? So is this everything that I have to know about the path? What about, I don't know, taking another iterated integral or something? But it turns out that this theory is telling you that if your limiting path is alpha elder for alpha larger than 1/3, And in the Brownian motion case, this is the case, right? So Brownian motion is 1/2 minus Helder. And if you have this case, then it's enough to know 2 levels. You don't need a 3rd level. So the 3rd level is going to be a continuous function of the first 2 levels. What I'm telling you is that if you know this 1st and 2nd level in the limit, you know all the paths. So there is nothing that you can extract more than that using graph path theory. It tells you everything from that perspective, at least.
Okay, any other questions? Okay, if not, thanks very much again.